Thank you. Okay, so we're going to be looking today at the curved arrow convention, which basically is using a language to account for how chemical reactions, particularly organic chemical reactions, occur. We had done some lectures recently where we looked at mechanism, and we said that mechanisms indicate sort of a moving picture of how reagents are converted into product, that mechanisms are burdened with the responsibility of identifying any and all intermediates along the pathway, indicating when they form, when they decompose. Mechanisms also have to identify the rate determining step of the reaction. And we did some faceless things with, A plus B gives C, and then C might be converted into D, and then D might be converted into E, and so on. So they were sort of faceless things, and we had some kinetic analyses that would help us identify which mechanisms were inconsistent with the data, and so you could ignore those. And then which mechanisms were consistent with the data. And I would make the point that at the end of the day, organic chemists are very careful about saying that this is the mechanism. The best you can do is say that this mechanism is consistent with the available data. We're less comfortable saying that this mechanism is correct. There's an old joke that rate over mechanism is equal to fact over fiction, right? You can't argue with the data. You can't argue with the kinetics. But the mechanism you put from the kinetics, so that's a bit more nebulous. The best you can do is say the mechanism is consistent. What we're going to do today is talk about what happens when we have actual molecules. So it's not an A plus B gives C, and then C decomposing to give D. We're not doing that. We're going to look at individual molecules and how they react, and the language of how we describe the conversion of reagents into products. To do that, we're going to be acquainting ourselves with a concept that we've used already, and that's curved arrows. There are two types, we talked about this in one of the very early lectures, that in organic chemistry in particular, there are lots of different arrows that mean lots of different things. And each type of arrow means something very specific. So for example, this means that A and B are in resonance with each other, but that neither A nor B exists. The true entity is a weighted average of these. So it could be somewhere here where it's very A-like and less B-like, or it might exist somewhere here where it really is a true mixture of A and B. It's half and half. Or it could be very B-like. But it's not true A, it's not true B, and it's not true A. Whereas this statement is something entirely different. Right? That means A and B are real. And if I put A under the reaction conditions, at the end of the reaction, there's about half A and half B. But A and B are real. That is not the same statement here. So the arrows in chemistry mean very specific things. The arrows we will be talking about today are the curved arrows, and they come in two forms. There is the curved arrow, which is a full-headed arrow. Now, that can be drawn like this, or it can be drawn like this. Right? So those are equivalent. It doesn't matter whether I cross the head of the arrow. So this is a full-headed arrow, and that is distinct from this, which is often called the fishhook. And whether I cross it here as I did there, or I leave it uncrossed, it doesn't matter. This suggests the motion of what's called double electron transfer. In other words, it's 2-electron transfer. We are moving 2 electrons. And this describes single electron transfer. In other words, we're moving one electron. Okay? The tail of the arrow represents the source of electrons. So the tail of the arrow is the source. That's where there's a region of high electron density, often a region that is negative, or it can have lone pairs, or it can have pi pairs. Okay? So the tail of the arrow describes a region of high electron density, or source. The head of the arrow represents the region of low electron density, that is the sink. And electrons flow from an area of high electron density to an area of low electron density. Vis-a-vis, they flow from the source to the sink. Now, I'll make 2 points here. Point 1, this is not unusual. Whenever there's a potential difference, something flows in order to minimize the potential difference. Ideally, to remove the potential difference. So if I place a hot object in contact with a cold one, heat flows from hot to cold until the temperatures are the same. If I have a region of high pressure and a region of low pressure, wind flows from high pressure to low pressure to equalize the pressure differential. The reason we get, if I know a lot of chemistry and you don't, information flows from the high chemistry potential to the lower chemistry potential. And the reason we get electricity is that I have electrons that flow from the negative pole, the high electron density pole, to the positive pole, right? The low electron density pole. And if I connect them by a wire, then the electrons flow through the conduit. So it is the nature of the universe that something flows from a region of high pressure to a region of low pressure. And we're describing, and that's what chemists do, we're describing electron flow. How do electrons move? But the other point I make is, in the lecture we've looked at before about mechanisms, A, B, and C, by faceless things, we couldn't tell who was electron rich and who was electron poor. They were faceless, we couldn't make any decisions about them. What we're about to embark on is a journey in which we're going to look at a molecule and decide, is that molecule electron rich? Is it a nucleophile? Is that molecule electron poor? Is it an electrophile? And sometimes in the same molecule there are electrophilic sites and nucleophilic sites. And we have to make judgment calls based upon electrophilicity, nucleophilicity, acid-base parameters, which reaction goes and which one does not, or if any reaction goes at all. So our understanding of Lewis structures becomes of great value because we have to be able to look at a molecule and determine whether it is electron rich or electron poor. So let's go ahead and jump in. And I will just say, for example, we've seen curved arrows with 2 electrons before. So when we're looking at building Lewis structures, we may have had something like, if I look at carboxylate maybe. So in a carboxylate, I can draw a resonance form that looks like this, right? And I end up with this species. Okay? And we use our arrows for that. What we're saying is, we're moving 2 electrons from this O, dumping them between the O and C, making the pi bond. So a lone pair becomes a pi pair. And then we move the pi electrons onto this O, so a pi pair becomes a lone pair. Right? We've done resonance before, or if I have something like this species, right? And I have something like that, or we've seen cases where we do this sort of resonance forms, and we end up with this entity, right? So we've got some familiarity with using curved arrows in the past. That lone pair of electrons becomes a pi pair, and pi pair becomes a lone pair. And if you notice, we're bound by certain boundary conditions. I can move the electrons from atom to the bond in which it's attached, atom to the bond. I can move bond to atom, bond to atom. Okay? With resonance, we were only concerned with the motion of lone pairs and pi pairs. And it must be that case because the feature of resonance is that we're not moving atoms, right? We're only just moving electrons. If you break a sigma bond, you're moving atoms, okay? So resonance was only featuring the motion of pi electrons and lone pairs of electrons. When we do chemical reactions, that involves bond breakage and bond formation. So we're going to be cleaving, in addition to pi bonds, we'll be cleaving sigma bonds as well. But I bring this up to show that we have some familiarity with the mechanics of moving electron pairs. Right? We've been doing it since the third or fourth lecture. Or second or third lecture when we talked about resonance forms and Lewis structures. So this is not entirely new. Okay, so I'm going to start this, my first look at mechanisms, by looking at the reaction between, say, hydroxide ions and HCl. And I want to ask the question, I'm going to ask two questions. Question one is, what do I get? And question two is, how do I get it? Okay, now, there are two different exercises happening. When we do mechanisms, normally what happens is, I give you the two reagents, I give you the product, and I ask you to tell me how does it form. So the role of mechanism is to describe how the reagents go into product, which means you must have the reagents and the product. You can imagine the mechanism as being the meat of a story. So I can say, there was a woodcutter who had two children, Hansel and Gretel. That's my reagent. My product is the end. So, and they lived happily ever after, the end. Well, all of the meat of the story is missing. That meat is the curved arrow mechanism. The curved arrow mechanism describes how we go from the beginning of the story, the reagents, into the product, right? Which is, or the end of the story, which is the product. So that's one thing happening, which is the more important one for this discussion. The other one, which we would have talked about already in the acid-base lecture, is, you look at this and you have to ask, well, for example, both of these could be acids because I have H attached to O and H attached to Cl, right? I would have to ask the question, well, if this lost the H to that, am I generating a stronger acid or a weaker acid? And then if this lost the H to the hydroxide, is the chloride ion a stronger or weaker base, for example, than hydroxide? So we spent some time on that discussion before. That's not going to be a major part of our discussion now. It will pop up, which is why we did acid-base before we did mechanisms. But let's see how we go. So I know what happens. Hydroxide reacts with HCl to give water and chloride. It would help me to maybe draw water like this, which gives me a better visual of which bonds are being made and which bonds are being broken. So clearly what is happening is, this O is protonated by that H. So I'm going to make an OH bond, and I'm going to break an HCl bond. So I'm making a mental laundry list, a to-do list of what is happening. We are going to make an OH bond. We're going to break an HCl bond. Okay. Well, bonds require 2 electrons. And I have to ask myself, well, fine, where are the electrons for the OH bond coming from? And the answer is, they will have to come from the electron-rich entity. Well, who is that then? Who is the nucleophile in this reaction? Who is the electron-rich species? Well, for heaven's sake, I've got an O with a negative charge on it. So that O, I will argue, is the source of electron density. The H is the sink. Right? So the electrons are going to flow from the O to the H. Now, if you notice, I am putting the electrons between the O and the H. And why am I doing that? Well, because that's where they end up. I'm not putting electrons on the O. I am putting them between H and O because I'm making a bond. So the 2 electrons on the O, which are a lone pair, are being used to make a bond pair, a sigma bond pair. Okay. Well, that takes care of one of the items in my laundry list. Make the OH bond. When I look at the H has a duplet. It already has a share in 2 electrons. When I bring these 2 electrons in, the H can't have a share in 4. H is an element in the first period. It has access to the 1s orbital and the 1s orbital only. It can hold 2 electrons, right? It's got 2 electrons. Which means if I bring these 2 electrons in, the H is now going to be exceeding its duplet. That can't happen. So as I bring these electrons in, the H must relinquish its hold on these 2 electrons. And I'm going to break the HCl bond and dump the electrons in the Cl. Well, I'm going to ask myself 2 questions. Question 1. Is this reasonable? Well, I know it has to happen. Because that's why I have the product. The product is telling me where I need to go, and this is a reasonable pathway to it. Well, it's a pathway to it. Is it reasonable? Well, let's see. What would compel the O to attack the H? The O is electron rich. Look at it. It's got a negative charge. And it's got 3 lone pairs on it. Why would the O attack the H? Well, the H is attached to Cl. The Cl is very electronegative, much more so than the H. So the Cl has been sucking electrons from the H, creating a delta minus charge on the Cl and a delta plus charge on the H, and a significant one at that. So it makes sense that the electron-rich, in this case negative O, would be attracted to the delta positive H. That makes perfect sense. It also makes sense that this HCl bond cleaves, because the Cl has been sucking the electrons from the H from the get-go. So as these 2 electrons come in, the H is all too happy to dump the electrons in the Cl and give it what it's been pulling from it anyway. It's been asking for electrons from the get-go. All we're doing is giving it what it asked for. In fact, I can look at it another way. I can say what is happening here in this bond formation, bond breakage, is a push and a pull. There are 2 electrons on this O that are involved in the chemistry. Those 2 electrons, as they approach the H, are pushing the electrons in the HCl bond. So the incoming electron density from the O is pushing the electrons in the HCl bond towards the Cl. That's a push. But there's also a pull. Because the Cl is more electronegative than the H, it is pulling the electrons towards it. And look, chemistry and Kuroda mechanisms is about the motion of electrons. If I ask you to move the podium, It's harder for me to move the podium if I stand behind it and push, or if you stand in front of it and pull. I can do it, but it's easier if as I push, you pull. That makes perfect sense. Things move more easily if they're pushed and pulled. Well, so do electrons. Just like podium, well, a podium or podia, right? Things move more easily if there's a push and a pull that are happening in concert with each other. So this makes sense to me that the electron-rich O, in this case the nucleophile, attacks the electron pore H, which is electrified, the electrophilic site. These two electrons are used to form the OH bond, and I'm going to break the HCl bond. Okay, now let's figure out my charges. There's a 1 minus charge on the left and a 1 minus charge on the right, so we're charge balanced, and we're also mass balanced. Even if I don't put the lone pairs of electrons around this Cl, and even if I didn't put them around the O, and we talked about this very early on with Lewis structures, I know that if this O is negative, that means it's got a lone pair, it is giving 1 electron to that H in the formation of the OH bond. If I am negative and I'm losing an electron, I end up being neutral. This Cl has invested 1 electron in the HCl bond. The other electron is H's. This action gives the Cl both electrons, the one it owns and also H's. So this Cl is getting an electron. Well, if I'm neutral and I gain an electron, I'm going to be negative. So often with mechanisms, I won't draw the Lewis structure. I could, right? And sometimes I will have to. But if I have the charges, I can use the charges on the reagent species to identify the charges in the product. Okay? But by doing an assessment of, you know, as I donate an electron pair, I'm essentially losing an electron. And as the bond breaks and I get the electrons, I'm basically gaining 1 electron. So this is the curved arrow mechanism for the reaction. How do I do it? I look at my product. I make a laundry list in my head of what has to happen. I can ask myself, I can do the curved arrows to make it happen, and then I have to have a higher level assessment of, is what I've drawn reasonable? Does it make sense? Right? Electron rich attacks electron poor. Push, pull, right? And the last thing I'd look at is, how does this jive with my understanding of acid-base rules? Well, strong base is giving the weaker conjugate base. That makes sense. The strong acid is giving the weaker conjugate acid. And that makes sense. Right? We talked about acid-base chemistry last lecture. So the way we do mechanisms is we look at our reagents or products, figure out who went where, which bonds were made, which bonds were broken. Engineer the bond breakage and the bond formation using the curved arrows, and make a high-level judgment call. Is what I have drawn reasonable? Is it consistent with acid-base rules? And what are the acid-base rules? Strong makes weak. Strong acid will give weak acid, never the other way around. Strong base gives weak base, never the other way around. Okay. Well, let's look at another one. So suppose we're looking at the reaction between chloroethylene and cyanide, and my product is acetonitrile plus chloride. So I've got cyanide attacking chloroethane, and the product is propanonitrile and chloride. Okay, first things first, make a laundry list. What has happened? Well, we have done a substitution reaction. This carbon, the alpha carbon, in my reagent was bound, in my substrate, the organic molecule is the substrate. The alpha carbon in the substrate is bound to chlorine. In the product, it's bound to Cn. So I've replaced a Cl by Cn. And I expelled chloride. So I am making a carbon-carbon bond, and I am breaking a carbon-chlorine bond. Well, what are my options? If I'm going to make a carbon-carbon bond, where are the electrons coming from? What is my source? Who initiates the process? The electron-rich species, right? I'll say that, and we'll talk about it in some more detail later on, but we can look at this as the electron-rich species being the aggressor. Okay? Who's the aggressor? Well, that would have to be cyanide. Clearly, it's electron-rich. And I can argue, carbon is not very electronegative. So carbon with a negative charge is not a happy chemical. It is willing and ready to get rid of the negative charge because it doesn't like having it. It's not particularly electronegative. So I can see some desperation in the carbon to get rid of the electron density. Where's it going to put it? Well, if that's a nucleophile, what site in this molecule is electron poor? And the answer is, well, that carbon. Why? One answer is because that's where the Cn ends up. I know that's where it has to go, so that must be where it's going to attack. Right? I'm using my product to inform what I believe is happening in the reaction. But that makes sense though, because this carbon is attached to the Cl, which is very electronegative, drawing electrons from it, creating a positive dipole on the carbon, and of course a negative dipole on the Cl. So it makes sense for the cyanide, electron-rich, to target the electrophilic site in the substrate. So I'm going to draw this mechanism as follows. I'm going to say, here is my chloride, here is my cyanide. The cyanide will use the electron pair to form a carbon-carbon bond. This carbon has an octet, right? I didn't draw them, but it's understood that there are two H's here. So this carbon has a sharing 2, 4, 6, 8 electrons. When I bring these electrons in, the carbon can't hold 10. It must therefore relinquish its hold on 2 electrons. Well, which 2? Well, not these, right? Because if it were those, my product would be H minus. I'm not losing H minus, right? That's not what the reaction is telling me. I'm losing Cl minus. So I know that what has to happen is we're going to do a concerted break of the carbon-chlorine bond. And besides, losing H minus is a very strong base. We can't have a weak base make a stronger base. So when the cyanide attacks, I can't lose H. One, I can't lose H minus. One, because it's a very strong base, and two, because that's not my product. Your job in doing a curved arrow mechanism is to account for how reagents as given make product as given. And that's it. There's no H minus being lost here. So we're not even going to entertain that. So my cyanide is attacking this carbon, I break the carbon-chlorine bond, and that's going to give me, I'm using my lone pair to make a carbon-carbon sigma bond. Right? So this is the carbon of the cyanide, and I would have lost in the process Cl minus. And is it reasonable? Absolutely. That's electron rich, that's electron poor, match made in heaven. Modestly strong base, very weak base. Because HCl is a mineral acid, it's a very strong acid, which means the conjugate base is pathetic. Okay? HCN is a modestly weak base. I'm sorry, HCN is a modestly weak acid, which means the conjugate base is modestly strong. Strong base gives weaker base, that obeys my acid-base rules. So that's a mechanism for the reaction. There's an alternative. The alternative is maybe this doesn't happen in one step. It could potentially happen where I do bond breakage first, and I lose chloride, and I end up with what would be a carbocation. And then the carbocation would be attacked by cyanide, and that's going to give me my product. So that is an alternative mechanism. Maybe the bond formation and bond breakage aren't concerted processes. It's not a one-step process. Maybe it's a two-step process. Okay, well, let's examine it. If I do this, I make a carbocation that is a primary carbocation. Right? Because the alpha carbon only has, here's my alpha carbon, only has one alkyl. Methyl and primary carbocations are impossible to form unless the primary carbocation is resonance stabilized. So unless you're dealing with a carbocation that is benzylic, so you can do resonance stabilization, or allylic, so you can do resonance stabilization, or maybe it is attached to a heteroatom like O, so I can do resonance stabilization. Unless you can stabilize a primary carbocation by resonance, it's not forming. That is an unstabilized primary carbocation, which means we are not forming that. So this mechanism is impossible. So we are looking instead then at a concerted process where the cyanide attacks the haloalkane, I make my propanonitrile and chloride in one step. Now, I could ask you, sketch the reaction profile diagram for this reaction. Well, I'm asking you to do two things. I'm asking you, well, obviously I'm going to have enthalpy against reaction coordinate. If I ask you to sketch the reaction profile diagram, what am I asking you? I'm asking you two things. One, is this a one-step, two-step, three-step, 10-step process? Question one. And is the reaction endothermic or exothermic?